Hello and welcome to Through the Telescope, the podcast that puts the lens on astronomy. I'm Rose Waugh and I'm an astrophysicist and science communicator.
And I'm Elliott Bruce, and I'm neither of those things, but I'll be trying to find out why we should even care about astronomy. We'll be exploring some of the big topics in the field in little manageable pieces and have some fun along the way.
So, whether you know your red giants from your redshifts, or you're not quite sure what the difference between astronomy and astrology actually is, join us as we launch ourselves into the cosmos and try not to burn up on re-entry. Through the Telescope is sponsored by Pic Astro, the astronomy and astrophotography image sharing app, dedicated to your images of the cosmos no matter what stage you are on your journey around the universe. No ads, spam, or fake accounts.
So, Ro, today we're talking about red dwarfs or M dwarfs?
M dwarfs.
M dwarfs. Okay.
Mm-hmm.
So, what are M dwarfs?
M dwarfs are a spectral type of star that are very small stars.
Okay.
So they're very small stars. If you want the more hardcore jargon, I suppose, then they are a spectral type that are defined by strong titanium oxide absorption, which is seen in the red end of the light spectrum that the star gives out.
Okay.
The red end, but the optical light.
So they've got a fair amount of titanium oxide in them compared to other stars, I guess.
Yeah.
Yeah. So I normally think of stars just as being all hydrogen all the time.
Yes.
But no.
Well, I'll let you in on a secret. So do I.
Okay. Phew.
So, all of my models of stars that I work on, they're just hydrogen.
And is that valid?
Depends what you want to do. It's valid for what I care about.
Okay.
But stars are mostly hydrogen. Astronomers will describe anything that isn't hydrogen or helium as a metal.
Yes, we have mentioned that shocking definition
Fake
before.
news. Stars also contain some of these other metals, i.e. things that aren't hydrogen and helium. And the amount of certain things that they contain varies between different types of star.
Yes.
But really, it's quite valid to just think of M dwarfs as very small stars.
Okay, so how small are we talking?
Well, the biggest ones are about 0.6 that of the Sun, mass-wise.
Okay, right, so
pretty small.
Yeah.
The smallest ones are about 0.08 solar masses.
That's a big range.
And that limit essentially comes from how big it needs to be in order to still be a star.
Right, so below that we do then have brown dwarfs.
Yeah.
Right, okay.
Yeah.
So 8% of the Sun is kind of the point where fusion actually starts.
At that point,
Fusion of
because I
helium,
care about
hydrogen.
stars, I like to compare it to the Sun. And so I know these numbers in terms of solar masses.
Okay.
Masses of the Sun, whatever you want to think of it as. But really, when you're down at the lower end of 0.08 solar masses, you could equally well consider that mass in terms of Jupiter masses.
Right, okay.
You know, it's going to be relatively big, but it would be a number that makes sense to use, if you know what I mean. So they really are small. Especially, the sun is, I guess, big. But for a star, it's not really that big.
I mean, if these are the smallest
So-
stars, or the set of the smallest stars, and the biggest ones are 60% of the sun, it's not... The sun isn't massive compared to that.
Yeah, exactly.
It's the same kind of...
It's not really... It's obviously a notable difference, and there are physical consequences. But in the grand scheme of things, it's still kind of similar.
So if they are smaller, and some of them are barely fusing, does that mean they're also cooler?
Yes. That is what they're literally described as in the literature. Cool stars.
Nice.
You'll remember that conference?
I remember you went to a Cool Stars conference, and I wasn't entirely sure whether they had made that themselves to be like, hey, this is the Cool Stars conference. It's not like the other Stars conference where the cool kids.
Yeah.
But is that actually just a...
Well, I don't know why they picked that. I mean, I want to say, yeah, it's because it's all about cool stars as in cold stars. But, I mean, when you look at the logos for these conferences over the years, it's like there's a couple of conferences that use cool stars, and it'll be like a picture of the sun with sunglasses on or something, and you're like, oh, this is so cringy.
I guess at least they don't have a baseball cap on or something. Apologies to anyone listening wearing a baseball cap. I am not a good indicator of what cool fashion is.
No, it's not even that. It's just that cringe thing of trying to be like,
yeah,
we're cool.
Yeah, I think that's it for me. It's when you see kids' TV and it's like, hey, what up? We've got rapping going on and we've got caps on backwards, and it's like, I'm not even sure that was cool in the 90s, but sure thing.
So yes, they are cool in the cold sense.
Okay, but you didn't go to the Cold Stars conference. Because that's a different kind of vibe, I guess.
Yeah, I've never been to a cold stars conference, but there's still time, I guess.
Yeah, I guess so.
Surface temperatures are about 2,000 to 4,000 degrees Kelvin.
Okay, so that's pretty... At that point, it's not that far off 2,000 to 4,000 degrees C,
Yeah.
which I guess is 4 to 8,000 Fahrenheit, roughly.
I trust your conversion.
I think you can pretty much double it when you get above a certain point. Not quite.
So they're pretty cool.
Yeah.
A lot of stars are 5,000, 6,000.
Yeah.
And you get some that are considerably hotter than that. But, it's definitely at the cold end of the spectrum for stars.
Yeah, I mean, in furnaces, not even particularly advanced furnaces, it's 1,200 Kelvin or something like that. So it's not that far off,
Yeah.
temperatures we can relatively easily make on Earth. I say relatively easily. I could not do that, but some people can.
But some people have the skills. Yeah. So these are, not temperatures in the core of these stars, but where temperatures that are used as a way of comparing between different stars.
So I guess they're small, they're not that hot. That doesn't make it sound like we're going to be, they're the brightest candles in the candle shop.
Yes. The star that burns the brightest burns the fastest and all that.
Yeah.
Yes, dwarfs are the opposite of that.
Okay.
They don't burn particularly brightly. And they burn for a really long time.
Okay.
I use the word burn, slight
Fuse.
cringe, but
But
yeah, they're not that bright. You can't really see them with the naked eye. You need a telescope, really. They're pretty faint. And because of their temperatures and things, they're easier to see at the more infrared side of the spectrum
Okay.
of light. than in optical.
Right, because infrared is lower energy than visible, which is
Yeah.
lower than UV and X-ray, etc. So we can see them at the lower end of the...
Yeah, at the lower energy part of the light spectrum. Yeah.
Okay. But they last a while then, if they're the opposite of the star that burns twice as hot, burns half as long.
How many variations of that saying?
I don't know. Has anyone ever said star? I'm not sure. Is that...
I don't know. Yes, they can. There's a whole range of ages of them.
Right,
But-
just as the whole range of masses and...
Yeah, but they can live a very long time.
Okay.
So, stars that are, lower in mass tend to live a really long time. It takes them longer to evolve throughout their different life stages.
Okay.
So, if you had a star that's about 0.16 of a solar mass.
Okay, so 16% of the sun.
Yes, thank you. I'll let you do do that for me. Which is an M dwarf. This would have its main bit of life, its main sequence, for about 2.5 trillion years.
Okay, and once it gets to the end of that, that's when the star starts dying, right?
Yes, so stars go through life cycles where they are, they're formed, they start to turn into a star, and once they have reached a certain point where they are no longer sucking up material from around it, which we call accreting.
Nice.
Once they are no longer accreting any material that's around them, and they're fusing, properly, then we say that this is like the beginning of their life as a star.
Right, okay.
So that's often called zero-age main sequence. And at that point they go on to the main sequence, which is the main bit of their life. And when they get to the end of main sequence, that's kind of colloquially, that's kind of the end of their life.
Right.
That's them starting to die, if you like, which often takes a very long time. It's not like it happens very quickly.
Yeah.
So for this star, this 16% of the sun star that we're talking about, they'll be on main sequence for 2.5 trillion years.
That's a long time.
Which is a really long time.
Again, that'd be an American trillion. So
And yes.
10 to
course it is.
the 12? Times the 12, maybe.
And then after that, the next bit of their life, the first bit of their dying process,
Right. The first bit of death. 1 foot in the
will
grave.
last them 5 billion years.
Okay. So
At which
compared to
point
the main
they're
sequence
a blue
bit.
dwarf.
Ooh, okay. So they're in the main sequence. They're living their best life for 2.5 trillion years.
Yeah.
And then it's only 5 billion or so. 5 million, sorry.
5 billion.
Okay. Yeah. So we've then significantly less. We've gone from trillions to billions. Okay.
Yeah. So,
Yeah.
just to see how many people were paying attention
Okay.
to what I was saying. How old is the universe?
Very old. I would say it's about the lifetime of the universe. Plus or minus 10%.
Come on, the kiddo knows the answer to this question.
Oh, jeez. Well, if a star, if it's going to be on the main sequence, is it trillions of years?
No.
Oh, okay, right. Well, let's see. I was born in the 90s, so
Yeah, there are different estimates, but it's not really. It's the order of magnitude that matters. We don't need exact,
hundreds of billions of years.
It's about 14 billion years old.
40. Okay, that's pretty young. When you use the word trillion, it kind of.
So, this star...
This 16% of the sun.
Yeah.
Is going to live for... Once it starts, it's going to live for 2.5 trillion years.
Yeah.
And there's only been 14 billion. So, like, less than 1,000th of that time.
So even if the star started at exactly the beginning of the universe...
I'm guessing it didn't?
Which it didn't. But,
Okay.
Even if our hypothetical star did...
It's like 0.1% of its life.
Yeah.
Already.
It's still got a really, really long time.
No, you weren't kidding about them being like... It's taking the whole candle burning analogy to...
Yeah, to the extreme, right? So, yes. Basically, because of this, there aren't any dwarfs that are in the later stages of evolution.
Right, okay.
Because the universe just isn't old enough.
So does that mean when you said that, and then it'll take however long to become a blue dwarf, do we know what a blue dwarf is? Because I guess that means one doesn't exist yet.
Correct.
So we've just sort of not guessed, but you know what I mean? Like, there's no evidence. We've just, I guess, taken it from other stars and been like, this is going to end up doing this.
Yeah, so I mean, we know what other stars do. For some stars, that's more meaningful than others.
Right, okay.
So if you look at what like a massive O-type star does, or a massive B-type star, which if you've listened to
Our stellar classification.
Then we might have mentioned them in a bit more detail. I'm going to be honest, I can't really remember because that feels like so long ago. But we did talk about stars.
And it was O, B, A, F, G, K, M.
Well done. Yes,
so we're talking about M dwarfs.
Yeah.
So they're at the lowest end. Right, it's biggest to smallest.
Yeah.
So O and B are the most massive.
Yeah, they're the chunky boys.
M is the smallest.
Yeah.
So you're saying that in the case of the biggest stars...
Yeah, if you look at them...
Yeah.
And you say, oh yeah, I know exactly how their entire life works out. That's not really going to help you.
Right, yeah, we're talking about chalk and cheese.
You can't really, like, extrapolate that and say, oh, this is what dwarfs are going to do. But we do know about stars, that are closer to dwarfs.
Okay.
That aren't that much more massive. And you can take that whole list of letters that you read out.
Yeah.
And you can kind of say, some of these are high mass stars, and some of these are low mass stars.
Right, okay.
And so anything that's above, like F and above, really, that's a pretty high mass star. Some of them much more than others.
Right, yeah.
If you've got a G, which is, the sun is a G type, a K or an M, they're all low mass stars. And whilst there is variation between those different types, there are a lot of similarities.
Right, yeah.
Of things that behaviours and characteristics that low mass stars have or that high mass stars have.
And can you start to kind of draw a trend of like, oh well, G is like the biggest of the low mass stars and it does something, but then K does something that's kind of related as it's smaller. It's a bit different, but it's similar.
Yeah, I mean, a lot of their behaviour is really quite similar.
Okay, you don't even need to like draw a line.
So basically, what it comes down to is what the interior of the star is like.
Okay.
So when we talked about the sun, we talked about all the different layers in the sun.
So there was a core and a radiative and a convective zone working outwards.
So if you have a high mass star, then you have your core, and then you have a convective zone, and you have a radiative zone on the outside.
Okay.
And you have other things, but the idea is that energy transports from the center outwards
Okay.
in that order.
Mm-hmm. Mm-hmm.
If you have a low mass star, then you typically have a radiative zone on the inside and a convective zone on the outside.
Okay.
The convection on the outside gives you the granulation that you see on the sun.
Yeah, that's the you cooking your pasta sauce and the bubbles up on the top.
Yep.
Yeah.
The reason I say typically is that for some M dwarfs, they don't have a radiative zone.
Is that like they've got a radiative zone which is 0 thickness?
Which we will come back to.
Okay.
But the point is that between high mass stars and low mass stars, energy is transported differently
Okay.
out from the star, and that influences
How it
a
ages.
lot of the behaviour.
Okay, yeah.
There's other stuff going on, but so you can kind of think about low mass stars, and you can kind of think about different spectral types and get ideas about how low mass stars in general will behave.
Yeah. So we've had, they're pretty small, they're pretty cold, they're cool, they're not very bright. They are going to outlast everybody.
Yeah.
I guess
They're in it
most
for the
stars
long
are,
haul.
but yeah.
They are very common when we look around us.
Okay.
They're the most common star. They are about 70% of the stars that we see. And
Okay.
possibly more. Because they're faint,
You
it's
can't.
difficult to see.
Hmm.
There is a plot out there
Oh,
somewhere
I love a good plot.
for people interested, which you might be able to find.
Does it have a name?
I don't know if it has a name, but it's relatively famous, so I feel like it might come up on Google. I suppose I could search for it. And it is a histogram. So
Okay.
it's basically the y-axis, the vertical axis is number of stars.
Number of observed stars, is it? Or
Yes, these are observations. And the horizontal axis, or x-axis, is like star mass, star
right? Okay.
type. And there's a peak at lower stars. Interestingly, there's actually a little bump. So you might think it would start. You might understandably think, and scientists would agree with you, that it would start off at a maximum and then decrease.
As
so
mass
that,
increases.
Yeah, so that the more massive it is, the harder it, the less common it is.
You've got to have the right amount of stuff there to make such a massive star in the first place. So.
Exactly. And this is pretty much what we see.
Okay.
But not quite, because the lowest of the low are actually slightly less numerous than ones that are a little bit heavier, but still very low mass. Maybe there's something funky going on, but probably this is because the smaller it is, the fainter they get, the harder they are to see. And so it's probably a bias of our capabilities.
So sampling issues.
Because, if you're trying to make something small, you need less stuff. So
based on mass alone, is that why they're very common? Or do we have to worry about how we get there in the first place? If we just have a little amount of stuff hanging around, we'll get an M dwarf. Or do we need to worry about there need to be the right conditions to make an M dwarf?
Yeah, so at the very beginning of the universe, well, I guess at the very beginning of the universe there weren't any stars, but when stars started to form, we think that they were like all high mass stars.
Mm.
There was a lot of stuff around, and so they would have formed into big stars.
And that was like
And that
hydrogen.
would have been pretty much all hydrogen.
Okay.
As time goes on, fast forward a whole bunch of time, because we can't sit around waiting for the universe to happen. We'll be here forever, literally. And these stars that have gone through their life cycle have turned hydrogen into helium, and also some other stuff.
Okay.
Some of the metals. That
Including
astronomers
the
like to
metals
talk
that are
about.
metals.
Including metals that are actual metals, and some metals that aren't metals.
Right, yes.
And so then there's a whole bunch of stuff around that isn't just hydrogen.
Right, yes.
Given that M stars are a spectral type that have titanium oxide
Yeah, they've got
in them, they've definitely got stuff that's not just hydrogen. So probably weren't there at the beginning.
Right, yeah.
They're probably going to get more common as the universe ages as well, because you need less stuff to make them.
Yeah.
And as stuff starts to get further and further away, because the universe is expanding, it becomes increasingly difficult to make anything, and therefore easier to make an M dwarf than a big star.
Yeah. Yeah.
So you do need to worry about what's around, I guess, if you want to make M dwarfs that we see.
But they're still the most common things that we see.
Yes.
So we've bundled all of these different stars from, like 8% to 60% of the mass of the sun into one nice handy M dwarf labelled bucket.
Yes.
So does that mean that these all behave perfectly identically the same and are, just wonderfully labelled?
Yes.
Okay.
Nah,
No.
I'm kidding.
Right.
Nah.
Why is that never the case?
Well, the fact that you need to ask
Yeah.
goes to show.
You've burnt by
Because
this before.
humans like to classify things into a box that makes sense for their current purposes.
Yeah.
And doesn't necessarily fit every purpose.
Yes. Yeah, it fits my purpose right now. It's not going to fit your purpose, especially not if your purpose is going to be like 20, 30, 50 years later.
And that's not my problem.
Not my problem.
Yes. No, they don't all behave in exactly the same way.
Okay.
But I think especially because M dwarfs are they're at the boundary.
Right, yeah.
They find the box more difficult to stay in than if you picked a different star, like a G or whatever type star, where it's more kind of mid-sized star. It's not like in terms of masses, but in terms of the spectral types, it's it's more comfortable.
Yeah.
And so the difference between one end and the other of a G-type, the lowest G-type you could get and the more massive G-type you could get, is not going to be as significant.
As something that is barely a star.
Yeah.
And something that is
Definitely a star.
much closer to being the mass of the sun.
Yeah.
Which I think people are pretty happy with being a star.
Yes.
Yeah.
So this really is partly what makes them so interesting, I think.
Okay, because they're not just M dwarf. Now that I know it's an M dwarf, I know exactly what's going on.
Yeah. don't. They don't behave like you want them to. I've found this in my own research. You think, I have a bunch of M dwarfs. That's great. They're all the same type of star.
Mm-hmm.
Fantastic. I'm going to put them on a plot, and they're not going to do what I want. You're like, oh, great, that's a trend. And then there's a whole bunch down here that are just like, no. No. And then if you look at the bunch that don't want to do what you want them to do, that don't want to follow the trend that all the others are following, it's probably because they're the lowest mass.
Right, okay.
And the others are like comfortable that they're a star.
Right, yes.
And those ones, I don't know, they've got some sort of imposter syndrome that they're not really a star, you know?
Yeah, there's like a sliding scale of starness.
Yes.
Yeah. Okay.
So
what?
as we mentioned earlier,
Okay.
M dwarfs are a low mass star, so have their radiative zone inside and then the convective zone outside of the core. So the convective zone is near the surface, and that's great. And then if you go to the smallest M dwarf, they don't have a radiative zone.
You're right, so it's just like
They're
core,
fully convective.
then convective. Okay.
So how they transport energy is different.
Very different.
So when we talked before about how high mass stars and low mass stars are different because they transport energy differently, you then find yourself in the same
Right,
thing
yeah.
again. There's
yeah.
now a different regime. Also, age influences it as well.
Okay.
So stars that are earlier in their life,
Okay.
still M dwarfs on main sequence, but if they're earlier in their life, then their energy transport is a bit different to when they're later in their life as well. So they don't really act, exactly the same as each other. They go through this kind of change.
Yeah.
Where everything is just a little bit different. And the magnetic fields change as well. Partly because of all the motions.
Right. Okay, because again, moving charged particles, magnetic fields is that kind of the... You always manage to bring it back to magnetic fields.
Yeah. I always bring it back to magnetic fields because I love them. But yeah, so some of them have more complicated magnetic fields, and some of them have really simple magnetic fields.
Right, so there's the difference between the classic bar magnet and something really scary.
Yeah. And how strong their fields are can also change. So some have kind of stronger and more complicated magnetic fields, and some have magnetic fields that are really simple in the sense that they're like a dipole bar magnet, pretty much exactly, and they're quite weak.
Okay, that's odd.
And yeah, these ones can be a bit funky.
Because without thinking about anything at all, I would just think small stars that are sort of just qualifying as stars, and a little bit more, but still like low on the scale of stars, should be like relatively weak when it comes to everything. So like not much light, not much in the way of magnetic fields. I would just feel like everything is...
Yeah, I mean,
the power's way down.
mostly the lowest mass ones are pretty weak and simple fields.
But I just find it crazy that you can have
But
like
sometimes,
a sort of, such a big
they're
change
not.
between like that.
Yeah,
It just seems...
yeah. I mean, the ones that have stronger fields aren't anything crazy because they're still low mass stars. But yeah, there's a lot of variation that goes on in M dwarfs, because they're not really one cohesive group.
Right, yeah. Is it...
Because again, you're classifying something in a way that makes sense for some purposes, but it doesn't for all purposes.
Is it related to how quickly they spin or something?
No, it's more just how big they are.
Okay.
And therefore what their interiors are like.
Okay.
I mean, how fast they spin is important. But rotation rate is often or can be a proxy for how old something is, how old a star is. Because stars are spinning at a certain rate, and then that starts to speed up because they're accreting, they're collecting material from around them.
Right, okay.
And that gives them angular momentum,
gives
them energy and speed, if you like.
Yeah.
So they start to spin faster, and then they have a wind like the sun does, and that's blowing material out all of the time away from the star. And over time, that means that then the star starts to slow down because it's losing energy and material, and so it slows down until it reaches some point. And so you can kind of age something from its rotation rate.
Yeah, so that's that classic kind of figure skating or any other spinny thing. So if you had like...
Office chair when you're bored.
Yeah, you pull stuff, if you're spinning and you pull something in towards you, you speed up.
Yeah.
And that's when you're accreting, you're pulling stuff in towards you, and then you throw stuff out over time, and so you start to slow down. Because the thing you've just thrown out has taken some of your angular momentum with you.
Yes.
Kind of idea.
It's taken some of your speed away so that it can speed away.
So they're all a bit... They've all got their own little foibles, and they're all a bit different.
Yeah.
And they've got their own
They
character.
got character.
Is that in any way related to why you won't let me call these red dwarfs? Is that a different term? Is that for like a subset of...
Yeah, not really. Red dwarf is not really a well-defined term.
Right.
First of all, I am eternally irritated by the fact that that's what the Wikipedia page uses.
Right, okay. Because you're a true researcher, so...
So I spend a lot of time on Wikipedia. They have used it to mean M-dwarf.
Okay.
I think, from what I can gather from the page. But it isn't a well-defined term at all. It can be another name, but it can also mean all M-type and K-type stars.
Right.
And a K-dwarf or K-type star is slightly bigger than an M-dwarf. So if you remember O, B, A, F, G, K, M. So K is bigger than M-dwarf, but smaller than the sun.
Right. Are we a K-type?
Who?
The sun.
No.
We're a G.
It's smaller than a sun, which is a G.
Sorry.
Yeah.
Okay. So red dwarf can mean some things, including K and M.
So red dwarf really means it's red.
Okay.
And it's a dwarf.
And dwarf is...
Small.
Is it smaller than the sun, or like...
Yeah.
Okay. And then you can then
I have seen some people talk about G-dwarfs.
Okay.
Now, I don't really know, like, if that's a term. Like, it's not something I've seen very often. I don't know if they specifically mean, like, really small G-stars.
Why do we need to talk...
Or what? It's not a common thing. But my point is, red dwarf just means it's red and it's small.
As stars go.
It doesn't really mean anything.
Right. Whereas a K-dwarf is a K-type star, which is small, which presumably is all K-type stars, and an M-dwarf is a small star, which is an M-type, which again presumably is... So is it, when we say M-dwarf, is that actually specifying the type of dwarf star as opposed to specifying the type of M star, if you see what I mean. Like it's a M.
Yes, so all M-type
Dwarf star.
stars are dwarfs.
Yes.
Yes.
Because you could just say an M star.
You could just say an M star or an M-type star, yeah. And some people do.
Okay.
But most people don't.
Okay. So we might have G dwarfs, we've got K dwarfs, M dwarfs, and they are all maybe possibly by some people called red dwarfs, and then below that we've got brown dwarfs, which don't count as stars, unless
Yes.
you like to count them as stars.
Yes. Yes.
Okay.
Yeah.
Right.
So a G-type star isn't a red dwarf.
Okay.
First of all, G-type stars like the sun are not red.
Are they an orange dwarf?
Yeah, they're yellowy orange, aren't they?
Okay.
Whether they're a dwarf or not, I guess maybe that's dependent on who's talking. Because again, that's not really it's not like, that's not a well-defined term.
Yeah.
So I guess you could use that for whatever you want, depending on your purposes. But that's why I don't like the term red dwarf.
Okay.
It
Just
doesn't.
because it's not.
It doesn't
useful.
really mean anything. And not only does it not really mean anything, but different people use it to mean different things. So you read it and you, like, I don't know what you're talking about.
Yeah. Do you think there's more?
Although it does make me think of the TV show.
Yeah, I was going to say, do people maybe want to keep that as a term more now that there's a TV show from the 90s?
Yeah, possibly.
So you said that they have magnetic fields that can be more crazy than you might think, and some of them are similar in size-ish almost to the sun, 60% of the sun at the upper end.
Yeah.
You're moving your head like, no, not really.
I mean, what does that really mean? It's similar to the sun, yeah, in some ways. Like, everything's relative, right? So yeah and no.
But so, should we be expecting, are these going to have coronal mass ejections or prominences or sunspots or any of these things? Flares?
All those things.
All of them. That's just what stars do.
All those things.
Okay. And can we expect planets around these things?
Yeah, we can definitely expect planets. Probably if you... I mean, I guess you don't need that much leftover stuff, but if you have an M dwarf, you probably start off in a region of space with less stuff than bigger stars.
So you're not expected to get a huge amount of planets.
And they're probably going to be smaller as well. Not necessarily, you're unlikely to get an M dwarf with like 5 Jupiters going around it.
Right, okay. Because basically that's enough to add to make a proper star.
Yeah, exactly. Exactly. But yeah, there are plenty known with exoplanets. ESO's HARPS. There's a HARPS north and a HARPS south.
Okay.
High accuracy radio velocity planet searcher. HARPS.
Okay.
They published a study in 2012.
Okay. 10 years ago.
Yeah, I was going to say, which actually is quite a long time ago now. And it suggested that 40% of M dwarfs had super Earths, which are 1 to 10 times the mass of Earth.
Okay.
Within the habitable zone. So 40% is relatively high.
Yeah.
But the same study found that less than 12% have heavy planets like Jupiter and Saturn.
Right, okay, so it does seem to be skewed that way. And also, I guess what we were talking about before, especially with the exoplanets episode, it's easier to find larger planets.
Yeah.
So, if anything you would expect to see it the opposite way around, if there was a sampling bias, if you know what I mean.
Right, yeah, and that's why hot Jupiters, which is a term that probably a lot of people have heard.
I've heard of that one.
Quite famous because they are Jupiter-like planets in that they're big gas giants. And they're hot, so they're close to the star. So they're, like, easy to spot.
But I guess,
Yeah.
like you were saying before, the nature of M dwarfs maybe means that we can't be completely happy with 40% and 12% as like super accurate values.
Yeah. I mean, I don't know which point you start to feel like these things are super accurate. I don't know how many, this was, like you say, this was like 10 years ago, so I don't know how many points they had in this study. It'll have been considerable because it's a large scale study, but I don't know what it's like, in comparison to now as well, because they will have done lots of follow-up things. HARPS is still going strong.
You said north and south. What is this? Is this in space? Is this on Earth? What does the north and south mean?
Northern hemisphere and southern hemisphere.
Okay.
But because M dwarfs are smaller, it's easier to find like a 1 Earth size planet around an M dwarf than it is to find it around a bigger star.
Right.
Because that Earth size planet passing in front of the star is blocking out considerably more light, more surface area than it would on a bigger star.
Yeah.
So
if you had a supermassive star and then Mercury went in front of it, that would be the same as like a bit of dirt in front of your telescope.
Yeah.
It's like a 1% thing, and it's probably noise. Whereas like a giant Jupiter, especially one close up, a hot Jupiter, it's like, wow, I've just lost like 100% of the intensity coming from that star.
Yeah.
And in the case of M dwarfs, there's not that much intensity to start with, so, and they're quite small, so a little Earth goes in front of it, it cuts off. In the case of the light curvy.
Yeah, so they, these kind of planets, smaller planets, are easier in that sense to find than they are on other stars. But with that said, M dwarfs are very dim in the brightness sense. So it is difficult to know how representative these kinds of studies really are.
So are there any that we should know or already do know? Are there any famous M dwarfs?
Well, we know of lots, but I think the most famous one is Barnard's star.
Barnard. Like Barnard's Castle.
I was going to say exactly the same thing, like Barnard's Castle.
Which became very famous in the UK.
Infamous.
Yeah, relatively recently. But anywho.
So yeah, if you want to check your eyesight, you go to this star.
Right, yeah.
It's the 4th closest star to us.
Okay.
Actually, that we know of anyway.
What's the closest one?
Well, Alpha Centauri is actually a trinary.
Right, so when you say it's the 4th closest, it's basically the 2nd closest, because the 3 closest stars are all in one place.
I mean, that is true, however, I would say that's a matter of opinion, however you want to define it.
It's true, but it's also really not true, because there are 3 stars over there. They just happen to be all next to each other. Yeah.
It's relatively small.
Okay.
It's 0.14 solar masses.
Okay, so 14% of the sun by mass.
Yeah. Its radius is 0.2 solar radius, which equates to about twice the radius of Jupiter.
Oh, okay, right.
Yeah.
Right.
Yeah.
See, that makes it feel, I guess it's a volume thing, and it's like radius and volume, there's a cubed relationship.
There is, yeah.
But when you say that a star is twice the radius of Jupiter, it feels like
Uh-huh.
Jupiter's not that far off being a star, but okay.
I mean, Jupiter is far off being a star, but I know what you mean.
Yeah.
Yeah.
I don't feel like you should be able to have a Jupiter in a picture next to a star and sort of just be like, that's twice as big. I mean, it's not twice as big, but, twice as wide. It doesn't feel right.
Yeah.
Okay.
It's really old. It's about 10 billion years old.
And you say that the universe is 14 billion. Is that right?
Yes.
Okay.
It's about twice as old as our sun.
Okay.
So it's possibly one of the oldest in our Milky Way. 10 billion years old.
Right, okay.
That said, it's not really that old for itself. Given that our hypothetical star that we talked about earlier was 16% the mass of the sun rather than 14%. And that's going to live for about 2.5 trillion years.
Right, yeah.
The star is 10 billion years.
So it's like, it's a toddler at this point, if that.
Yeah. Whereas the sun is middle-aged.
Yeah, right. It's just watching, I guess it's a bit like, other stars must be kind of like mayflies or something to it, It's just like, here today, gone tomorrow.
Tragic. So yeah. You were asking about activity on other stars.
Yeah.
So we've observed flares coming from the star.
That seems kind of crazy.
Which is quite cool. Yeah, I mean, so we have observed flares on lots of other stars.
Okay.
It's not like it's specific to this star, but that is a fact about this star.
We do know that it is active.
We know that it has flares and things like that.
Okay.
It rotates about once every 130 days.
Okay. Okay.
So
a third of a year.
That's pretty slow. For perspective, the sun takes about a month.
Right. Yeah.
About 28 days. So...
a fair amount longer.
Yeah, fair amount longer. It's rotating quite a lot slower than our sun is. People have suggested that it has planets, but so far we've not actually found any conclusive evidence of that.
Right.
People have, I think, suggested it with evidence rather than just saying
yeah,
star has
probably got planets.
But it's
always been found to be like that was like an issue
it's
with the
either
data
been
or
disproved
something.
or it'll have been just not replicated.
Right. Yeah.
And so it's then, probably not a planet because a planet is always there. So you should always see it.
Yeah.
Planet hunting is actually quite difficult. I mean, we're very good at it. We've found lots of exoplanets now.
How many so?
Over 5,000 that have been confirmed, and thousands more that we haven't yet confirmed. We haven't got two bits of evidence for. But as we've said before, it is really important to be able to replicate the results.
Yeah.
Because there can be lots of false positives. Things like the sunspots that you were talking about earlier, or stellar activity in general can create similar things in the data.
Something that blocks out the light a little bit, but it's actually a bit of the star which is colder or more dense or something passing in front of it.
And so it can look like there's a planet, but then because stellar activity changes over time, it's not a constant. If you go back and look again, it won't necessarily be there, or it'll look different. Whereas if it was a planet, it will always give you the same behaviour again and again and again at a very predictable amount of time from the previous observation.
It's not like the planet is going to go around, like, it's going to take a year to go around 1 year, and then it's going to take 2 years to go around the next time or something. It's like circular motion.
Yes.
So, M-dwarfs. What a weird bunch.
Yeah, they're pretty weird.
Not red dwarfs.
Well, they could be if you want, but not that long ago. So for any of our listeners that are not aware, I'm currently at the very end of writing my thesis, which feels like it's been the case for a long time. But life has made the last bit of my PhD take a lot longer than I thought it was going to take. And I truly am almost there now. I'm just waiting to get the edits back from my supervisor for my conclusion chapter.
Jeez.
And then after that, I'll have had a full first draft, and then I'll have a full second draft ready for my supervisor to okay my changes, and then I can submit it. So it is, almost there now. And it's been interesting because I've, revisited stuff that I did literally 5 years ago.
That you'd forgotten that you'd done.
And really kind of, because it's taken me so long to get to this stage, even though I started writing a really, really long time ago. It's taken so long to get to this stage with the thesis that I've had a lot of time to reflect on it. And a lot of space to reflect on it and the science that's gone into it. And if you'd asked me not that long ago, are M-dwarfs your favourite star? I would have been like, nah. Because there were bits of that project that just made me want to pull my hair out. Which is not fair because that's not on them. But actually, I don't know. I really do love stars that are similar to the sun precisely because they're similar to the sun. And I, like probably everyone on this planet, feel a bit emotionally invested in the sun. I feel
it's quite important.
I feel connected to it and interested in it, and it feels very significant to me, my experience of the universe. And therefore I care about other stars that are like the sun because I can learn a lot about what the sun would have been like when it was younger. Because I specifically like young stars. But equally you can learn a lot about what it will be like when it's older, which is also interesting because it feels connected to your life. But I do actually, as time has gone, I do feel like quite invested in M-dwarfs as well now because there's so much variety in one spectral type, and it's it's purely because of the way that we have classified it, really. But they are fascinating.
I think there's also something about the fact that they're pushing the limits of what a star is, but they're also going to be a star for the longest period of time imaginable. Yeah. And for me, they're pushing the limits of what a star is on the right side of the boundary. Lots of people are fascinated by brown dwarfs, and which are the sometimes called failed stars. They're not quite big enough to be a star. They're too big to really be a planet like Jupiter, even though they have similarities to planets like Jupiter. But they're too small to actually fuse hydrogen in the long term. So they make a bit of light and then they're just going to stop because they can't sustain it. They don't make a chain reaction. It's that kind of...
Yeah, the gravitational force is not strong enough to make the pressure big enough to sustain that reaction. So they'll make some, but then it can't keep going.
Yeah.
The chain reaction eventually stops. And loads of people are fascinated by them, and I'm mildly interested in them. You know?
Mm-hmm.
I'm more interested in stars. So M dwarfs are like on the right side of that boundary for me, whilst, like you say, they're on the boundary, which is anything that is on the boundary of anything is interesting, because that's where the magic happens. That's where the funky, weird stuff happens.
Well, thank you for telling us about the funky, weird stuff. I think we'll wrap up and talk to you next week.
Yes.
So that just about wraps things up for this episode. Please, can we encourage you to subscribe to Through the Telescope wherever you find your podcasts, and if you like, you can leave us a nice positive review as well. It really helps the show and it makes it easier for more people to find us.
Feel free to send us any comments, questions, or suggestions of things or people you'd like to hear about or from in future episodes. Or perhaps to put yourself forward to chat about your own astro research or experiences. As always, you can find us on Instagram at Through the Telescope Podcast, or you can find me at astrophysicist_Rose. You can also find us on Twitter at The Telescope Pod, and you can contact us by email at throughthetelescopepodcast@gmail.com.
And with that, we'd like to thank you very much for listening, and we look forward to seeing you again next time.
Bye.